Section 9.6 is vectors in space, which means vectors in 3 dimensions. So here is how we graph 3 dimensions. The x-axis is coming up out of your screen, and then your y-axis and your z-axis. There's something called the right-hand rule, which helps orient you in space in your 3 dimensions. Everything in 3 dimensions for vectors is pretty much exactly the same thing as in 2 dimensions. For instance, to find the distance formula in space, or to find the magnitude of a vector that's in 3 dimensions, it's exactly the same thing, your same Pythagorean theorem or your same distance formula. We just now add on the z direction. So go ahead and pause the video and find the distance between point P1 and P2. So if you end up doing the distance formula and then adding on the z direction as well, you end up with -1 minus 4 quantity squared, 3 minus a -2 quantity squared, and 2 minus 5 quantity squared, which ends up being the square root of 59. So now we have vectors in 3 dimensions. We now have a k-hat. So if you want to find a position vector, then it's the same thing as in 2 dimensions. If you're given a starting point and an ending point, then you just find the difference between them to find your position vector. So go ahead and pause the video and find the position vector v that represents the vector p1, p2. So to find position vector, you subtract each component. So you get 4 minus a -1, which is 5i hat, 6 minus 2, which is 4j hat, and 2 minus 3, which is -1k hat. So all the adding, subtracting, and multiplying by a scalar of vectors is all the same. So if you want to add 2 vectors, you just add each set of components. Now there's just a third set. Same with subtracting vectors. Multiply by a scalar, same thing, just multiply each component by that scalar. And then the magnitude is just the distance formula or the Pythagorean theorem in 3 dimensions, so we have to add on that third dimension. So we have v being 2i hat plus 3j hat minus 2k hat, and w being 3i hat minus 4j hat plus 5k hat. So go ahead and pause the video and find a, b, and c as well as the unit vector in the direction of v. So for a, multiply each component of v by 3, you get 6i hat plus 9j hat minus 6k hat. For b, multiply each component of v by 2 and each component of w by 3 and then subtract them. So you end up with -5i hat plus 18j hat minus 19k hat. For c, magnitude, Pythagorean theorem in 3 dimensions. So 2 squared plus 3 squared plus -2 squared, square root of that, you end up with the square root of 17. For the unit vector in the direction of v, it's v divided by the magnitude of v. We already found the magnitude of v up here, the square root of 17. So it's just the vector v divided by the square root of 17. So you end up with 2 over root 17i hat plus 3 over root 17j hat minus 2 over root 17k hat. So just like in 2 dimensions, dot product, you just multiply each set of components, the x components, y components, and z components together, and then just add them. So go ahead and, given v and w, pause the video and find a, b, and c. So for a, you end up with 2 times 3 plus 3 times -4 minus 2 times 5, so you end up with a -16. For w dot v, you could have either done the whole thing again and also got -16, or you could have remembered from 8.5 that v dot w is equal to w dot v. Since you already did this, you could have just also said it was -16. And then v dot v, you could have done this whole thing out, or you could have recognized that this was the same vector from the previous slide, and that any vector dot itself is just the magnitude squared. So we found the magnitude on the previous slide was square root of 17, so this was just 17. So when you're doing these, you can either do the whole thing out, or for some of them, you can remember the properties. So if you've already done v dot w, then you can just remember that w dot v is the same thing. So the direction angles of vectors is something new for 3 dimensions. Direction angles are the angles between the vector and each of the positive axes. So if you have angle alpha, that's the angle between v and the positive x-axis. Beta is the angle between v and the positive y-axis, and gamma is the angle between v and the positive z-axis. So if you're given a vector v, ai hat plus bj hat plus ck hat, then the cosine of alpha is equal to a over the magnitude of v. So alpha again was the angle with the positive x-axis, so the angle with the x-axis is equal to the x component over the magnitude. cosine of beta, or the angle with the y-axis, is equal to the y component over the magnitude, and cosine of gamma, or the angle with the z-axis, is equal to the z component over the magnitude. So it's always x angle, x component, y angle, y component, z angle, z component. It has a property that the cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma is equal to 1. So if you're given two of the angles, let's say you're given alpha and beta, you can then find gamma using this property. So if we're given v to be negative 3i hat plus 2j hat minus 6k hat, and we want to find the direction angles of v, the first thing we need to do is find the magnitude of v. So go ahead and pause the video and find the magnitude. So negative 3 squared plus 2 squared plus negative 6 squared, the square root of all of that, you end up with the square root of 49, or 7. So if we want to find the angle with the positive x-axis, or alpha, we have the cosine of alpha is equal to a, or the x component, over the magnitude of v. So that would be negative 3 over 7. So then alpha is equal to the cosine inverse of negative 3 over 7. And make sure when you plug this in your calculator's in degree mode. So if you plug in your calculator cosine inverse of negative 3 over 7, you end up with 115.376 degrees. So now beta, the angle with the positive y-axis, is the cosine of beta is equal to b, or the y component, over the magnitude of v. So go ahead and pause the video and find beta. So you end up with the cosine of beta is equal to 2 over 7. So beta is equal to the cosine inverse of 2 over 7, which is 73.398 degrees. So if you haven't already done so, go ahead and pause the video and find gamma, or the angle with the positive z-axis. So cosine of gamma is equal to c over the magnitude of v, which is negative 6 over 7. So gamma is equal to the cosine inverse of negative 6 over 7, or 148.997 degrees. So now you have the direction angles for all three of v. So now, the second example, if we have a vector v that we don't know, and it makes an angle alpha equals pi over 3 with the positive x-axis, and beta equals pi over 3 with the positive y-axis, we want to find the acute angle, gamma, that it makes with the positive z-axis. So if you remember from the previous slide, there was a property that related the cosine of the three angles together. So go ahead and pause the video and find gamma, the angle with the positive y-axis. So the property says that the cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma is equal to 1. So I know that alpha is pi over 3 and beta is pi over 3, so I plug those in. The cosine of pi over 3 is 1/2. 1/2 squared for both of these is 1/4. So you end up with cosine squared of gamma is equal to 1/2. Square root both sides, you get cosine of gamma is equal to 1 over the square root of 2, which is the same thing as root 2 over 2. I know that if it's a acute angle, it has to be in quadrant 1, so I only want the positive answer, not the negative answer on these. So then where in quadrant 1 does cosine of gamma equal root 2 over 2? Well, that means that gamma is equal to pi over 4. So when you're in 3 dimensions, everything from 2 dimensions holds. The only thing that we added are these direction angles. Make sure you always relate x angle with x component, y angle with y component, z angle with z component.